Hi all, welcome back to my YouTube channel. So now we are starting one new series that is phase locked loop PLL, and this is the first lecture of this series. Okay, so let's start. So the PLL, what is the use of PLL? Okay, so PLL is used for frequency generator. Okay, so it can generate any type of signal. It will be periodic only, but it can be of different shape. It can be square waveform, sawtooth waveform. Okay, so that is one function of the PLL. Now the second function is phase alignment. Okay, so the use case of PLL we'll see in further lectures. So first let's go to the basic operation of the PLL. Let's make the block diagram of the PLL. So the PLL contains one PD block, then it contains low pass filter block, and then it contains VCO. Okay, so it give output V out, there is V in, and then this output is coming as feedback to the PD. Okay, so this is the block diagram of the PLL. So what is PD? PD is nothing but phase detector. Okay, detector, and LPF is low pass filter, and then VCO is voltage controlled oscillator. Okay, we will go inside the block. We will try to understand its circuit also, and we'll implement it in future. Okay, and we'll simulate this PLL. So, but before that, let's see the operation of the PLL. So let your V in is equal to A in sine omega in T. Okay, and V out is A out sine omega out T. Okay, this is a different frequency at input, and output you're getting a different frequency. Okay, so you have this phase at input, this is phi in, and output you have this phase, that is phi out. So what is your phase error? Phase error is phi in T, whatever phase we give at input of the PLL, minus phi out T. Okay, so we talked that the function of PLL is phase alignment to make it 0 or constant. So for that, what we will do, we will try to make it 0. So that we will do with the help of the feedback. Okay, so now let's go to the next slide. So okay, see this VPD, what it will give? It will give V error, and this will give VC, and this is V out. So this V error voltage is proportional to phi error. Okay, so what will happen? This PD will compare phase of this V in, okay, that is phi in, and phase of output, that is phi out, and after comparing it, taking the difference of it, it will give you V error, and your V error will be directly proportional to phi error. So this is the function of the PD. PD is phase detector. Okay, so let's go to the next slide. So in PD, what we saw that V error is directly proportional to phase error. Okay, that is PD, and this is phase error, and this is V error. Okay, so when we will remove this proportional symbol, so that we can do with the help of a constant called KPD. Okay, so KPD is a constant, and what is the unit of the KPD? You can see it is V error by phi error. So it is voltage per radian. Okay, so that is the unit of KPD. Okay, now let's try to draw this equation. Okay, so this is your phi error, and this is V error. So when the phi error is 0, then V error will be equal to 0, and it is linear. So it will go how? It will go like this and like this. And what is the slope? Slope is KPD. Okay, so that is your PD, means phase detector. Now let's see the low pass filter. Let's go back to the previous slide and see. In low pass filter, let's uh, consider its transfer function is LFS. Okay, and this is okay VCS, and this is VRS. We are taking Laplace transform. So what will be your LFS? LFS will be equal to Vc as the transfer function is output by input. What is input? V error by S. Okay, understood. So this is LPF, low pass filter, in which the loop filter transfer function is equal to LFS equal to VCS divided by V error by S. Okay, now the remaining block is VCO. VCO is voltage controlled oscillator. Okay, so this is the VCO. It is getting the input VC and giving output omega out, V out. Okay, which is containing omega out frequency. Okay, you can see here that is the VCS is the input of the VCO, and you are getting V out, which is having omega out frequency. Okay, so now for this VCO, there is a relationship between V out and VC that is equal to omega out, then omega free plus KVCO dot VC. Okay, so this is the relationship between omega out and VC. Okay, so what is omega free? Omega free is called free running frequency. Let me write free running frequency. Okay, and what is this KVCO? KVCO is the gain of VCO. Okay, now you can see from this equation, if we are increasing VC, then omega out will increase. If we are increasing VC, omega out will also increase. So there is a linear relationship between the VC and omega out. Okay, so that let's draw this. Okay, so this is what is this? VC, the control voltage, and this is omega out. Okay, so now when VC equal to 0, what will be omega out? Omega out will be equal to omega free plus 0. That means omega out equal to omega free when VC equal to 0. So when VC equal to 0 is omega free. Okay, means your oscillator is running freely. That is called when there is no input at VCO, whatever frequency your VCO is giving, that is called free running frequency. Okay, means omega free. So now this is the frequency when VC equal to 0, and when you will start increasing the VC, your omega free will start increasing. Okay, so now what is the slope of this curve? Okay, what is slope? The slope is KVCO, y equal to mx plus c. So this m is the slope. You can compare this equation, these two. So this is your m, that is slope. So this gain is the slope. Okay, so now we know the basic function of PD. We know LPF. We don't know that why we are using LPF. Okay, so that we will know in upcoming lectures. And we know the basic knowledge about the VCO. Okay, so now the next is condition of PLL loop. Okay, what is the condition of PLL loop? As we saw our PLL block diagram, it was PD, then low pass filter. Let's write gain of that filter transfer function, I mean, and then there was VCO. This was omega out, the V out, you can say whatever you like, and then there was omega in, or you can say phi in also. There you can say phi out also. Okay, and it was giving to you V error, then VC, and this was phi out. Okay, then write here omega in or V in, whatever you want to write. Okay, but this PD is working on phi in. By comparing these two, phi in and phi out, it is giving you V error. Okay, we will see in upcoming lecture that how to design this PD. Okay, so now we know this, and we saw that in our first slide that it to phase alignment. What it means? So let your phi, your V in is there. Okay, and this is your V in. So it want to align this phase. Okay, between the this input and output. Okay, it want to align it. Okay, so like this. Okay, so you can see but this is a high frequency, whatever you want to take. Okay, so the phase between V in and V out, I mean phi in minus phi out, should be 0. When this thing will happen, we will call that PLL is locked. Okay, or you can say phi in minus phi out equal to constant, that is also okay. And in this situation we will call PLL is locked. This is also okay. So what we can say that phi error, differentiation of phi error by dt equal to 0, because it is constant, and this is what, this is phi error. So when you will take a differentiation of constant will be equal to 0. So this is one condition for PLL to be locked. Now your omega in should be equal to omega out. That is one another condition second. Okay, see in this waveform which I draw, see this rising edge, then there the rising edge coming. Okay, so there was a problem to compare this and this waveform. Okay, so we have to make this frequency equal to this frequency. Okay, so for example at input you are giving how much, let 1 megahertz you are giving, and output you are receiving 5 megahertz. Okay, then how you will compare this phase of this and this? For that you have to use one divider. Okay, so you use 1 by 5. So what you will get? 1 megahertz. So now let's draw at input. This is 1 megahertz frequency, that is V in, and then you got output also same. Okay. See, now you can compare. This is omega in, this is V out, this one waveform. It is omega out, which is equal to omega in. Or this waveform can be like this also. So the frequency is same, but it's shifted by some amount like this. Okay, same amount. Okay, so now this phi error, I mean this one, phi error, and I mean this phi error, this is phi error equal to constant. By constant amount it is varying, not like this. If it is vary with phi 1, some phase error phi 1, this is phi 2, this is phi 3, not like this. Constantly it is varying. Okay, this phi 1, phi 2, phi 3 all are equal to phi error, which is constant. Okay, so this is the PLL locking condition. So there are two conditions, again I am repeating. Okay, two conditions for PLL lock. So the very first condition, that is omega out equal to omega in. Okay. B, how we can do this? We saw that by using a frequency divider. Okay, that we can do. And what else? There is d phi error by dt equal to 0. Again, I'm telling you by with waveform. So if your this is omega in, I mean V in, which is having the omega in frequency, and your omega out is like this, shifted like this, and then it is like this. Okay. So now see, this is phi 1 and this is phi 2. Okay, so this phi 1 is not equal to this phi 2. So you can see phi error is not constant throughout the waveform of V out. Okay, but the frequency phi out equal to phi in, that is there. So in that case, this PLL is not locked. Okay, so your phi error should be constant. That is differentiation of phi error must be 0. Okay, this is the condition of PLL locking. Okay, now see, this is PD, then low pass filter, after this VCO, and there was a divider. Let's consider it is 1 by n. Okay, this is omega in, this is omega out. You can say phi out, and this is phi in. Okay. Now let's see, we have, there is a, by some reason, okay, there is a change in phi in. Okay, now the phi in increased by some amount, delta phi in. Okay, let's take some number. Let the phi in was 5. Now it increased by some amount, that is delta phi in 5.05, would increase somewhat. Okay, this happened. Just random number I'm taking. So because of this phi in, there was some VC was there, some V error was there. Because of that V error, there was some VC. And you got how much? Phi out you got. Okay, you got phi out. And now there is increment in this phi in, means phi in now become new phi in, that is become phi in plus phi in delta phi in. Okay, because this delta phi in, there will be increment is in this VC. Okay, then VRR will increase, then VC will increase. And you know that omega out was equal to omega free plus KVCO dot VC. Since this VC increased, this omega out is also increased. And you know that phi out equal to omega out dot T. Since this omega out increased, this phi out increased. Okay, so by same amount as this increased, this also phi out also increased. Okay, so there is no change in phase error. So phase error is still constant. Okay, let this phi out was 6. Okay, now the difference of phi in minus phi out is 6 minus 5, that is 1. Okay, now after increment what happened, this phi in become 5.05. Oh sorry, this is consider this is phi in, phi out you can consider 5, this you can consider 6, that is this like this. Okay, and this is 5, so it become 1 bigger number. I'm taking on 5 inside. So now this become this. Okay, so now there is same increment in phi out. Okay, after increasing this phi in due to this VC, same increment in phi out. So the phi in increased by 0.5, so it becomes 6.05. And similarly this phi in sorry, this phi out increased by same amount, that is 5.05. So how much it is? See, same. So you can see that phi error is constant only. Okay, so that is the use of this feedback. Feedback will compare phi in, phi out. By that, it will increase phi error, and by this, VC will increase, and after this, your phi out will increase, and in such way, it will keep phi error constant. Okay, and PLL will remain locked. Hope you all understand this. So, what we have learned today, we understand the basic block diagram of PLL. Basic block diagram of PLL. Inside that very basic function of PD, we have learned. Then low pass filter, we have to understand in more depth these all blocks. Then VCO, what is the equation? That is really important equation, that omega out equal to omega free plus KVCO dot VC. This is important. Okay, so this block we understand that why we need a frequency divider, that we understand, and what are the condition for PLL lock, that we have understood. So that was very basic. In upcoming lecture, we will go in more depth and we'll try to understand more about PLL, and we will design the PLL. So that's all for today. Thanks. Let's meet in next class. Thank you. Bye.